Bismillahirrahmanirrahim. Assalamu alaikum, ladies and gentlemen. We are to discuss a very serious and concerning topic of recent era. First of all, let me introduce to you my presentation team, which includes Muhammad Awais, Shahriyar Shahid, and Sayyid Muhammad Athar Tirimzi. Our topic of presentation is wastewater treatment. First, let me tell you what is wastewater. Wastewater is defined as water which carries wastes from homes, industries, businesses, or any other sources. It is usually a mixture of water and dissolved or suspended solids. A general question arises, why should we treat wastewater? Now, since water is becoming a scarce commodity, hence it is imperative to evolve technologies which treat them efficiently so that they can be reused. The principal objective of wastewater treatment is generally to allow human and industrial effluents to be disposed of without danger to human health or an acceptable damage to the natural environment. Treatment is also necessary because it helps in the reduction of physical, physiological, radioactive, biological, and chemical pollutants. This table shows the typical wastewater flow rates from various sources. Now we come to the types of wastewater treatment plants, which includes sewage treatment plants, sludge treatment plants, industrial wastewater treatment, agriculture wastewater treatment plant, radioactive wastewater treatment plant, recycling wastewater treatment plant, and plenty of more. Here are the names of some industries which have wastewater treatment plants, namely National Water Engineering Private Limited, Seaman Park Engineering Limited, Descon Engineering Limited, DDFC Private Limited, Duraclean Waste Management Services Private Limited, and EcoWest International Private Limited, etc. This is the process diagram of the basic steps of the wastewater treatment. Now we come to them one by one. First of all, we discuss preliminary treatment. The objective of preliminary treatment is the removal of coarse solids and other large materials often found in raw wastewater. Removal of these materials is necessary to enhance the operation and maintenance of subsequent treatment units. Preliminary treatment operations typically include core screening, grit removal, and in some cases comminution of large objects. In grit chambers, the velocity of the water through the chamber is maintained sufficiently high or air is used, so as to prevent the settling of most organic solids. Grit removal is not included as a preliminary treatment step in most small wastewater treatment plants. Comminutors are sometimes adopted to supplement coarse screening and serve to reduce the size of large particles so that they will be removed in the form of sludge in subsequent treatment processes. Flow measurement devices, often standing wave flumes, are always included at the preliminary treatment stage. This diagram shows the preliminary treatment and the process is grit removal. Now we come to the biological process, which is the conversion of settleable solids. In large sewage treatment plants, primary sludge is most commonly processed biologically by anaerobic digestion. In the digestion process, anaerobic and facultative bacteria metabolize the organic material in sludge, thereby reducing the volume, requiring ultimate disposal, making the sludge stable, and improving its dewatering characteristics. Digestion is carried out in covered tanks, typically 7 to 14 meters deep. The residence time in a digester may vary from a minimum of about 10 days for high-rate digesters to 60 days or more in standard-rate digesters. Gas containing about 60 to 65% methane is produced during digestion and can be recovered as an energy source. In small sewage treatment plants, sludge is processed in variety of ways including aerobic digestion, storage in sludge lagoons, direct application to sludge drying beds in process storage, and land application. The third step, ladies and gentlemen, is primary treatment. The objective of primary treatment is the removal of settleable organic and inorganic solids by sedimentation and the removal of materials that will float by skimming. Approximately 25 to 50% of the incoming biochemical oxygen demand, 50 to 17%, 70% of total suspended solids, and 65% of the oil and grease are removed during primary treatment. Some organic nitrogen, organic phosphorus, and heavy metals associated with solids are also removed during primary sedimentation, but colloidal and dissolved constituents are not affected. The effluent from primary sedimentation units is referred to as primary effluent. In many industrialized countries, primary treatment is the minimum level of pre-application treatment required for wastewater irrigation. It may be considered sufficient treatment if the wastewater is used to irrigate crops that are not consumed by humans or to irrigate orchards, vineyards, and some processed food crops. However, to prevent potential nuisance conditions in storage or flow equalizing reservoirs, some form of secondary treatment is normally required in these countries, even in the case of non-food crop irrigation. It may be possible to use at least a portion of primary effluent for irrigation if offline storage is provided. Primary sedimentation tanks or clarifiers may be round or rectangular basins, typically 3 to 5 meters deep, with hydraulic retention time between 2 and 3 hours. Settled solids are normally removed from the bottom of the tanks by sludge racks that scrape the sludge to a central well from which it is pumped to the sludge processing units. Scum is swept across the tank surface by water jets or mechanical means from which it is also pumped to sludge processing. Now we come to the next step, which is secondary treatment. The objective of secondary treatment is the further treatment of the effluent from primary treatment to remove the residual organics and suspended solids. In most cases, secondary treatment follows primary treatment and involves the removal of biodegradable, dissolved, and colloidal organic matter using aerobic biological treatment processes. Aerobic biological treatment is performed in the presence of oxygen by aerobic microorganisms, principally bacteria, that metabolize the organic matter in the wastewater, thereby producing more microorganisms and inorganic end products. Several aerobic biological processes are used for secondary treatment, differing primarily in the manner in which oxygen is supplied to the microorganisms and in the rate at which organisms metabolize the organic matter. High-rate biological processes are characterized by relatively small reactor volumes and high concentrations of microorganisms compared with low-rate processes. Consequently, the growth rate of new organisms is much greater in high-rate systems because of the well-controlled environment. The microorganisms must be separated from the treated wastewater by sedimentation to produce the clarified secondary effluent. The sedimentation tanks used in the secondary treatment, often referred to as secondary clarifiers, operated in the same basic manner as the primary clarifier described previously. The biological solids removed during secondary sedimentation, called the secondary or biological sludge, are normally combined with primary sludge for sludge processing. The final step is the sludge solids to further treatment and disposal. Common high-rate processes include the activated sludge processes, trickling filters or biofilters, oxidation ditches, and rotating biological contractors. The combination of two of these processes in series is sometimes used to treat municipal wastewater containing high concentration of organic material from industrial sources. High-rate biological treatment processes in combination with primary sedimentation typically remove 85% of the biological oxygen demand originally present in the raw wastewater and some of the heavy metals. Activated sludge generally produces an effluent of slightly higher quality in these terms of these constituents than biofilters or RBCs. When coupled with a disinfection step, these processes can provide substantial but not complete removal of bacteria and virus. However, they remove very little phosphorus, nitrogen, non-biodegradable organics, or dissolved minerals. Although secondary treatment can remove over 85% of biological oxygen demand, suspended solids, and nearly all pathogens, sometimes additional treatment is required. Some processes used in advanced wastewater treatment includes filtration, carbon adsorption, phosphorus removal, and nitrogen removal. Now we discuss them one by one. First we come to filtration. Sand filters similar to those used for producing drinking water are sometimes used for additional removal of microorganisms and other solids, unlike water treatment sand filters. However, the filter used in the wastewater treatment often use large, lightweight aggregates at the top to improve efficiency and facilitate cleaning. Now we come to carbon adsorption. The most practical way to remove refractory organics is by adsorbing them on activated carbon. Adsorption, not to be confused with absorption, is the accumulation of materials on an interface. Carbon is activated by heating it in the absence of oxygen. This activation process creates many small pores in each carbon particle. Activation thus increases the surface area of each carbon particle, making it more effective as an adsorption agent. The next is phosphorus removal. Phosphorus is wastewater is considered a pollutant because it encourages the growth of algae. Phosphorus removal usually involves the addition of ferric chloride, alum or lime to the wastewater, mixing it in a reaction basin and then sending the mixture to a clarifier to allow the phosphorus containing precipitate to settle out. Now the last is the nitrogen control. Nitrogen in any soluble form is a plant nutrient and may need to be removed from the wastewater to control the growth of algae. In addition, nitrogen in the form of ammonia exerts an oxygen demand and can be toxic to fish. Nitrogen can be removed from the wastewater by both biological and chemical means. The biological process is called nitrification or denitrification, and the chemical process is called ammonia stripping. In wastewater treatment, a term usually arises which namely terminal electron acceptor. Now, we know that microorganisms transfers electron from the energy source to the oxygen. In the process, oxygen and organic matter is converted to carbon dioxide and water. The oxygen is termed as the terminal electron acceptor. Microorganisms utilize some other oxidized compounds to accept electrons. In case of denitrifying microorganisms, nitrate serves as the terminal electron acceptor, as nitrate is converted to nitrogen gas. In this process, organic compounds are converted to fermentation products and carbon dioxide. In anaerobic digestion of wastewater solids, the fermentation products are converted to methane and carbon dioxide. Here are some examples of terminal electron acceptors. The process is given along with the terminal electron acceptor, the predominant reactions, and their examples. These websites have helped us a lot in gathering the data. Thank you very much, ladies and gentlemen. That's it for our presentation. I hope that we have provided you a little bit of concepts about wastewater treatment. Thank you very much.